Start talking about this idea of what it means for a function to be continuous as we talk about limits. And we're going to start off with a definition. All right. A function is continuous at a number C, I love saying that, at a number C, if, just because it sounds so funny, if the following conditions are satisfied. And I believe we have three of them. Okay, a function is continuous at a number C if the following conditions are satisfied. Number one, f of C is defined. That means there has to be an f of C. And we know there's situations where it's not. Okay, f of C must be defined. Number two, the limit as x approaches C of f of x exists. That's the second thing that must be true for it to be continuous. And then the third thing is that that limit, okay, the limit of that function as we approach C must be the value of the function there. Must be f of C. All right? So, sometimes this is really obvious, but let's just look at a very simple example and just show how it meets these three requirements. Okay? Let's say, for example, that I wanted to look at the limit. Well, let's not do the limit. Let's just talk about a function. We're just going to talk about a straight linear, something like this, 3x minus 5. Okay? And we know what this looks like. Straight line through negative 5. All right, we know exactly what this does. It's there. It goes up 3 over 1, up 1, 2, 3 over 1. So we're right there. Now, if I were to look at this function, let's pick a value, let's say 3. Okay? Let's say that C was 3. So the question is, does this function meet all three requirements? Let's go back to our original list. Number one, is f of C defined? Okay. Is f of 3 defined? It is, isn't it? 3 times 3 minus 5. 9 minus 5, it's 4. Okay, so if I were to come over here to 3, it would be 4. Okay, there's the point, 3, 4. All right, so it meets condition number 1. Number 1, smiley face. How about number 2? Number 2 said what? The limit as we approach C must exist. So, how about the limit as x approaches 3? Does it exist? That's all we need to answer. Does it exist? It does. Yes. Smiley face. Number 3. The third question. Does the limit as x approaches 3 equal f of 3? It does, doesn't it? Okay. Didn't we find out that f of 3 is 4? right? So right here's 4. As we approach 3 from the left, the function here is approaching 4. As I approach 3 from the right, the function is approaching 4, right? The left and right-hand limits are both the same. They're both 4. So we have met this condition as well. So this function is continuous at, what did we say? 3. Right? All right, let's keep going. I want to talk about several kinds of discontinuities. Sometimes it's better or more helpful to understand what a continuous function is by looking at what a continuous function is not. Okay? So, I'm going to give you several examples here. Example number 1. Let's say we have a function that does this. Has a hole at C. There's a hole there. That function is not continuous at C. Do we see why? Is f of C defined? Nope. F of C is not defined. This is what we call a removable discontinuity. Well, let's just abbreviate so we don't have to write forever. Maybe we'll write the first one and then the rest of them we won't. Discontinuity. Removable discontinuity. You know why it's considered removable? Because all I would have to do to make this thing continuous is fill in the hole. If I could define the function at C, it would no longer be discontinuous. Wouldn't it be continuous now? Right? If that were filled in. That's why it's considered removable. All right? That's the first kind of removable discontinuity. There's another kind. One like this. One that does this. This function, the way it is not continuous. Let's talk about why. Is f of C defined? It is. Okay. F of C is defined on this problem. But let's look at our rules. The limit as x approaches C must equal f of C. And it doesn't, does it? Think of our limit. Our limit is approaching here. So whatever this value is, I'll call it h. Okay? My limit right now is h as we approach C. All right? So this one is not continuous. All right? It's also called removable because if I could just move this crazy little point down here, then it would be totally continuous and it would be fine. All right? That's the second type of discontinuity. The next kind. This one's more obvious. This one's easy. That function is not continuous at C. And this one is called a jump discontinuity. Jump discontinuity. And I think you can see why it's called that. This one is obviously not continuous at C. The left-hand and right-hand limits are different, right? F of C is defined, but the limit is not f of C. So there's a bunch of reasons why this one is not continuous. All right? There's also what's called infinite discontinuities. Let's say this was C, and we had an asymptote at C. This one you should be real familiar with. and my function did this. Okay? That thing is not continuous at c, obviously. Or it could look like this. Maybe my function looks like this. One of those, kind of like the reciprocal functions. Both of these are considered infinite discontinuities. For obvious reasons. Okay? They're called infinite discontinuities. They're approaching infinity from the left and the right. All right? It's not defined at c. The function is not defined at c. It is infinite. One more that is not as common, and this is called the oscillating discontinuity. This is a function that is, I guess you could say, it kind of oscillates like crazy. Maybe it comes in right here and then it oscillates like crazy. It oscillates so fast that we're having a difficult time determining what it's how it is defined at a certain place, C, and we're having a difficult time determining what the left-hand and right-hand limits are. That one is not as common, but it is considered a type of discontinuity. All right? So in homework, they're going to ask you questions like this. What kind of discontinuity is this? They're going to give you a function. This one, a lot of them are going to be piecewise. I told you that we have to become real friendly with piecewise functions because they're not going away. So let's say that this was my piecewise function. And I wanted to know what kind of discontinuity this thing has. All right? So the first thing we need to do is graph it. Okay? So x cubed, we know what that does. X cubed goes through the origin. And it says it's x cubed up until 1. So right here is 1. And it says it's x cubed for x less than or equal to 1. So we will color in this circle. So there's the first half of my piecewise function. The second half is this thing, 3 minus x. That's the same thing as negative x plus 3. So that means there's a y, there would have been a y-intercept, okay, at 3. 1, 2, 3. There would have been a y-intercept, and my slope is negative 1. So I'm going to come down 1 over 1, and then it begins, and then it keeps going down 1 over 1. Now, if you do your piecewise function correctly, it should be pretty obvious, right? What kind of discontinuity is this? Jump. All right? So this is really more of an exercise in can I draw the piecewise function correctly? Okay? Now, let's look at the greatest integer function. Let's find the points of continuity. That means where it's continuous, and discontinuity, where it's discontinuous, for f of x equals the greatest integer function. All right? This is not as hard as what you might think it is. We need to get good at sketching this graph. All right, so let's just come over and sketch a little graph here. 1, 2, 3. We don't need to do a whole bunch of points. We only need a couple, really, because the function keeps going on and on forever. So we know that one is colored in and this one's open. And then 1, 2, 3. Then this one's colored in and this one's open. Colored in, open. Colored in, open. Same thing as we go down the other direction. Colored in, open, colored in, open. And remember how it's defined. Okay, we always go to the smaller integer. So for example, just to review real quickly, what would f of 2.5 be? 2. Okay, we always go down. What's f of 2? 2. All right? Now, but we can see on this function there's a whole bunch of discontinuous places, right? But is it discontinuous everywhere? No. No. Okay? Right in here, where the lines are, isn't it continuous? Right? So where is it discontinuous? At every what? Integer. Right? It is discontinuous, so guess what? We've already done one part of it. Okay? Number 1. This function is discontinuous at every integer. Now, the next statement. Where is it continuous? Or could we say every other real number? The integers are the only place where it's discontinuous, right? How about at 3.1? Are we okay at 3.1? Yeah. How about 3.01? Yeah, we're okay everywhere else except right at 3. So we can say it is continuous at every other real number. Or we could say every real number that is not an integer. Okay, if that makes you happier. Continuous at every real number or non-integer real number. Whichever way makes you feel warm and fuzzy on the inside. That's which way you can say it, so long as it's true. Now, one more thing. What if they ask you to find the discontinuities of some function? Like x squared minus 1 over x cubed plus x squared minus 2x. Something like that. They ask you to find the discontinuities. What did you just say? Well, we're not approaching infinity. We're not, we're talking about where could it be discontinuous. So let's think for just a minute. As we think of, isn't this a rational function? This is a rational function. Where are there problems with rational functions? When the denominator is equal to 0, which usually gives us some kind of asymptote, right? So this is a good review for us. How can I find vertical asymptotes? Set the bottom equal to 0. That's a great place to start. Set the bottom equal to 0 because I'm looking for my vertical asymptotes. So I need to take an x out, and now I have x squared plus x minus 2 equals 0. I need to do some factoring. X plus 2, x minus 1. Split all three of these up equal to 0. X equals 0. There's the first discontinuity, looks like to me. X plus 2 equals 0, so x equals negative 2. X minus 1 equals 0. X equals 1. Now guess what? All three of those places, is f of x defined? Is f of x defined at any of those three? No, it's not. So at all three of these, f of x is not defined, which means we cannot meet, my marker's having problems, we can't meet the first requirement for continuity. So we've already found three places. All right? Now, remember I told you on these problems, I told you that we are often going to verbally nag. Remember to do that. Remember to look at, which way did we look at it? Didn't we look at it analytically? Can't you also consider the graph? Can't you also go to the table? All right? There's a lot of things you can do with these problems to analyze if they're continuous or not. And we're going to stop there for today.